In early November of the year 2025, an anomaly defied the Sun's established order. 3 Atlas materialized from solar brilliance, an entity silent, compact, and resolute, appearing where astronomers anticipated utter disarray. Instead of the expected chaos, they encountered an unnerving stillness. There was no discernible tail, no nebulous coma, and absolutely no dust. It navigated the Sun's tempestuous environment as if impervious, showing no sign of distress. The Naves Observatory, alongside the Virtual Telescope project, corroborated the gravest fears of the scientific community: a comet that steadfastly refused to adhere to conventional celestial mechanics. Concurrently, at JPL, analysts observed perplexing data shifts. Transient illuminations, movements lacking any propulsive force, suggested an unseen influence guiding its course, transforming a seemingly ordinary comet into an enigma challenging the very foundations of physics. The fundamental question arose: was this phenomenon natural or something else entirely? Commentators such as Stefan Burns now advocate that it is not a comet in the traditional sense, but rather an ancient relic, dense and metallic, bearing the hallmarks of immense age and perhaps deliberate construction or intentional abandonment. Stay with me as we delve deeper, for if their hypothesis holds true, the pertinent inquiry shifts from identifying the origin of 3 Atlas to discerning the identity of its creator. If this enigma continues to captivate your curiosity as it has mine, please consider expressing your engagement by clicking the like button and subscribing to Cosmo Chill to ensure you receive every update as this unfolding event progresses in real time. Share your thoughts in the comments section, indicating your current location, the local time, and your perspective on this groundbreaking development. To foster the growth of this community, we encourage you to share this video across platforms like X, Facebook, Reddit, or even within your personal group chats. Your support is instrumental in enabling us to continue pursuing and presenting compelling narratives like this. Therefore, we extend our sincere gratitude for your unwavering backing. Part 1 commences with a pivotal moment. Envision this scene. Early November in the year 2025. Astronomers worldwide are poised, their sophisticated instruments focused on an object arriving from beyond our solar system. This entity, designated 3 Atlas, has just completed its closest approach to the Sun. A full week has passed since perihelion, that critical juncture where the Sun's intense heat should have transformed a typical icy comet into a spectacular exhibition of dust and gas. The Naves Observatory in Spain captures a photographic record, and the Virtual Telescope project in Italy replicates the effort. Scientists lean in to scrutinize their findings, and their initial observations elicit a profound sense of shock. The images reveal a mere point, a sharp, star-like pinpoint of light. There is no diffuse halo, no trailing tail extending away from the Sun, no luminous shroud of sublimating ice. Just a solitary dot against the vast blackness, as if an artist had placed a single pixel upon the cosmic canvas and declared their work complete. This is unequivocally not what anyone anticipated. It is essential to comprehend what was expected to occur. This celestial body reached its perihelion on October 29, 2025, at a distance of approximately 1.38 astronomical units from our star, translating to roughly 130 million miles, positioning it between Earth's orbit and that of Mars. For perspective, this proximity is sufficient for any standard comet laden with volatile ices, such as water, carbon dioxide, ammonia, and methane, to undergo significant heating. The Sun's radiative energy would vaporize these ices, releasing powerful jets of gas that would carry dust particles along. We should have observed a coma, that characteristic fuzzy cloud of gas and debris surrounding a comet's nucleus. We should have witnessed a tail, potentially stretching for millions of miles, propelled away from the sun by solar wind and radiation pressure. This is fundamental cometary behavior. It is what comets inherently do. 3 Atlas, however, appears to have bypassed this universal directive. The timing of these events further intensifies the perplexity. During the interval between October 29th and November 5th, when these images were acquired, the sun was far from quiescent. Recent solar flares had been bombarding the inner solar system with energetic particles and substantial radiation. Under such conditions, one would expect an amplification of outgassing, leading to even more pronounced activity than usual. Solar storms possess the capacity to ablate material from cometary surfaces, electrify dust grains, and generally generate a dramatic spectacle. Yet, 3 Atlas remains stubbornly star-like, refusing to exhibit any typical cometary displays. This brings us to the central enigma, the profound mystery that will occupy our investigation for the ensuing several hours. Why the absence of outward gas expulsion? Why no classic tail or dusty coma when all our established physical models predict their presence? Allow me to illustrate the predictions of the Standard Model. A volatile-rich comet approaches the sun. Solar heating intensifies. Ice begins to sublimate, a process where solid matter transitions directly into a gaseous state without an intervening liquid phase. This sublimation generates internal pressure beneath the surface. Eventually, jets of gas erupt through fissures, carrying accompanying dust particles. The gas coalesces to form the coma, radiating light as solar radiation excites its constituent molecules. The dust particles, propelled by solar radiation pressure, form a tail. Ionized gas, influenced by the solar wind, forms a second tail. Both tails generally extend away from the sun, creating the iconic cometary appearance that has been documented by humanity for millennia. This is the established protocol. This is how the process is understood to function. 3 Atlas, it seems, operates under a different set of rules, or perhaps none at all. This is not merely a quirky comet exhibiting slightly anomalous behavior. The discrepancy runs much deeper. We are potentially observing an object that challenges our fundamental classifications: icy comet versus metallic asteroid, or something entirely distinct. It is an entity that defies neat categorization within the frameworks we have developed to comprehend small celestial bodies. The implications of this single anomaly ripple outwards, akin to fissures spreading across ice. Our investigation will unfold in 3 distinct phases. In the first phase, we will establish the context, detailing the orbital mechanics, the photometric data, the observational timeline, and the core paradox driving this mystery. We will hear from various scientific perspectives, from those maintaining it is simply an unusual comet to those proposing far more extraordinary explanations. In the second phase, we will meticulously examine the anomalies and overlooked details, cataloging every peculiarity of this object and exploring the potential significance of each oddity. We will analyze compositional models, investigate acceleration mechanisms, and grapple with the perplexing question of its movement, which suggests material expulsion when no such expulsion is visually detected. In the third phase, we will broaden our perspective to connect this mystery with overarching trends in scientific discovery, space exploration, and artificial intelligence. This is because 3 Atlas does not exist in isolation. It is part of a larger narrative concerning the unexpected discoveries we are making across multiple astronomical frontiers. Here is what I urge you to keep in mind as we proceed. This presentation will guide you through evidence, anomalies, speculative theories, and interpretative analysis. Some of the content discussed is based on firmly established observational facts. Other aspects represent informed conjecture. I will clearly distinguish between the two. However, by the conclusion, you will likely find yourself contemplating a question you may not have anticipated seriously considering. Is this a comet or something far more peculiar? An entity originating from another star system, exhibiting behavior unlike anything observed in our cosmic neighborhood, something that might compel us to fundamentally revise our understanding of what interstellar visitors can be. And, for those with a particularly adventurous inclination, something that may not be entirely natural. Therefore, remain engaged, as what we are about to explore resides precisely at the intersection of the known and the unknown, between the explainable and the profoundly enigmatic. And it is at this boundary that the most compelling questions emerge. Part 2 presents the latest orbital and photometric updates. Let us establish a foundational understanding with concrete numerical data, as the trajectory of 3 Atlas tells a significant part of its story even before we address its unconventional aspects. This object is traversing our solar system on what astronomers term a hyperbolic orbit. While this designation may sound exotic, it simply signifies that this visitor is not gravitationally bound to our Sun. Unlike comets and asteroids that originated within our solar system and follow perpetual elliptical paths, 3 Atlas originates from an external source and is now embarking on its return journey into the void. It is a cosmic wanderer passing through our celestial neighborhood by chance. The Jet Propulsion Laboratory and the Minor Planet Center have been meticulously tracking this object since its initial discovery, refining their calculations with each successive observation. Its inbound velocity relative to the Sun's frame of reference was approximately 33 kilometers per second, equivalent to about 74,000 miles per hour, a speed that dwarfs any velocity achieved by human-engineered spacecraft. On October 29, 2025, it achieved perihelion at an approximate distance of 1.38 astronomical units from the Sun. Subsequently, it commenced its outward trajectory, gradually increasing its speed as it ascends the Sun's gravitational potential, ultimately heading toward interstellar space. However, velocity and trajectory are not the sole parameters being measured by astronomers. Photometric observations, which quantify brightness and color, have unveiled intriguing patterns. Since early October, observers have noted a significant brightening of 3 Atlas in the green wavelength band, approximately by a factor of 5. This is not a subtle alteration. It represents a dramatic amplification in luminosity at specific wavelengths, suggesting that either the object's surface or its surrounding envelope is reacting to solar heating. Green emissions from comets are typically indicative of the presence of diatomic carbon molecules, C2, which fluoresce green when energized by sunlight. Consequently, this brightening initially appeared as a promising indicator of cometary activity. However, as previously established, there is a conspicuous absence of a visible tail or a substantial coma to accompany this luminosity increase. The spectral signature suggests one phenomenon, while the visual evidence indicates another. Now, we must address the matter of non-gravitational acceleration, as this is where the situation becomes truly perplexing. When astronomers track an object's positional data over time, they can predict its trajectory based solely on gravitational forces, the pull exerted by the Sun, planets, and other massive celestial bodies. Nevertheless, occasionally, an object deviates from its predicted path, accelerating or decelerating in ways that cannot be accounted for by gravity alone. In the case of conventional comets, this non-gravitational acceleration arises from the reactive thrust generated by outgassing jets. Gas expelled from the sun-facing side of the nucleus imparts a slight push to the comet, akin to a miniature, inefficient rocket engine. This effect is well understood and routinely quantifiable. 3 Atlas exhibits clear non-gravitational acceleration. The radial component, representing acceleration directly toward or away from the Sun, measures approximately 1.1 multiplied by 10 to the power of -6 astronomical units per day squared. The transverse component, acceleration perpendicular to the Sun object line, measures about 3.7 multiplied by 10 to the power of -7th astronomical units per day squared. These forces are minute, yet undeniably real and measurable. Herein lies a calculation that is both illuminating and deeply troubling. If we postulate typical cometary outgassing, with gas ejected at approximately 300 meters per second, we can determine the mass that must be leaving the object to produce the observed acceleration. This calculation is contingent upon the object's mass, which can be estimated from its brightness and assumed composition. Upon performing the calculations, a startling result emerges. To generate this acceleration through standard gas ejection, 3I Atlas would need to shed approximately 13% of its total mass during the period of observation. 13%. Consider this for a moment. More than 1/8 of the entire object would need to be expelled as gas and entrained dust. This is not a minor outburst. It is not gentle sublimation. It represents a massive, sustained eruption of material that should be unequivocally visible to any telescope trained upon it. Such a significant mass loss would be impossible to conceal. The resultant dust and gas would form an enormous envelope around the nucleus, scattering and reflecting sunlight over a volume spanning millions of miles. It should be blazing in our images like a luminous beacon. Yet, we observe no such phenomenon. This is the paradox in its most stark mathematical formulation. The motion implies substantial mass loss, while the imagery indicates virtually no mass loss. Under conventional cometary physics, both cannot simultaneously be true. The observational timeline introduces another layer of complexity to this mystery. 3 Atlas was initially detected on July 1, 2025, by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes situated in Hawaii, designed to survey for near-Earth objects. However, this object was not in proximity to Earth in a hazardous sense. It was flagged due to its unusual motion relative to the background stars, motion suggestive of an object not gravitationally bound to our solar system. As news of its discovery disseminated within the astronomical community, major observatories began directing their instruments toward this visitor from beyond. The James Webb Space Telescope observed 3 Atlas on August 6th, utilizing its NIRSPEC instrument, the near-infrared spectrograph, which can dissect light into its constituent wavelengths to reveal its composition. The Hubble Space Telescope captured images, and ground-based observatories worldwide contributed data whenever observational conditions were favorable. Each subsequent observation contributed to the ever-growing dataset, and each observation confirmed that something unusual was occurring here. Or, more accurately, something unusual was conspicuously absent. The anticipated cometary activity, which should have been intensely visible, remained stubbornly absent, or at least undetectable by our instruments. This is not a single anomalous image from one telescope on a single night of poor quality. We are witnessing consistent patterns across multiple instruments, diverse wavelengths, and numerous observation dates. The statistical significance of this anomaly increases with each new data point. This phenomenon is real, it is reproducible, and it demands an explanation. Therefore, as we transition to a detailed examination of this paradox, keep those figures in mind. 13% mass loss inferred from acceleration, and virtually zero detectable mass loss from imagery. Between these two facts lies a chasm that conventional cometary science is finding profoundly difficult to bridge. Part 3 delves into the paradox in observational terms. It is imperative to establish a baseline for comprehending the true extent of 3 Atlas's peculiarity. The most effective method for achieving this is to revisit the characteristics of normal cometary behavior. You have likely seen depictions of well-known comets, such as Hale-Bopp with its luminous twin tails in 1997, or McNaught, which produced a spectacular fan-shaped display in the southern hemisphere in 2007. These celestial bodies serve as textbook examples of what transpires when volatile-rich objects venture into the inner solar system and are subjected to solar radiation. The process originates beneath the surface. A typical cometary nucleus is frequently characterized as a dirty snowball, or, more accurately, given the substantial dust content many possess, an icy dirt ball. While compositions vary, water ice generally constitutes the dominant volatile component, mixed with frozen carbon dioxide, carbon monoxide, methane, ammonia, and various organic compounds. All of these are intermingled with silicate dust and, at times, larger rocky fragments. When solar heat penetrates the surface, these frozen volatiles absorb energy and sublimate. The resulting gas does not escape uniformly. Instead, it erupts through weak points in the surface, generating jets that can be remarkably focused. Imagine them as geysers on a cosmic scale. These gas jets propel dust particles ranging from submicron grains to pebble-sized fragments. Once liberated from the nucleus, this expelled material forms the coma, a diffuse envelope that can expand to exceed the size of Jupiter. Despite the nucleus itself potentially measuring only a few miles in diameter, the gas within the coma fluoresces, meaning it absorbs ultraviolet light from the sun and re-emits it at visible wavelengths, producing that characteristic greenish or bluish glow. Concurrently, the dust particles scatter sunlight, generating a yellowish or white reflection that renders the coma visible even from Earth. Following this are the tails. Dust particles, driven by solar radiation pressure, form a curved tail that traces the comet's orbital path. This tail often appears yellowish-white, as it is essentially reflecting sunlight off minute particles. Simultaneously, the gas, having been ionized by solar radiation and the solar wind, is swept backward along magnetic field lines, forming a straighter, bluer tail that points directly away from the sun. Many bright comets exhibit both tails distinctly, creating that classic dual-tailed appearance that has historically instilled both fear and fascination in humanity. This is the established pattern. This is the behavior exhibited by volatile-rich comets when they approach the sun. The closer they get, the more active they become, until they eventually recede and the process reverses. We have observed this pattern hundreds of times with comets originating within our solar system. We witnessed it with 2I Borisov, the previous interstellar cometary visitor in 2019, which behaved precisely as predicted, brightening, developing a coma, and exhibiting outgassing activity that perfectly aligned with conventional models. 3 Atlas experienced the same solar heating that would trigger this cascade of activity in any typical comet. It passed perihelion at 1.38 astronomical units, well within the range where water ice readily sublimates. It encountered recent solar storms that should have amplified, not suppressed, its activity. Yet, when examining high-resolution images from November 5, 2025, 1 week after perihelion, when activity should still be vigorous, we observed that star-like point source, devoid of a substantial coma, lacking any visible tail, without a diffuse envelope, simply an absence of expected phenomena. Let us revisit that 13% mass loss calculation as it represents the mathematical core of this paradox. If 3 Atlas shed 13% of its mass through gas ejection at 300 meters per second, as is required to account for the measured non-gravitational acceleration, then fundamental physics dictates the fate of that gas and any accompanying dust. The gas would expand rapidly, forming a cloud around the nucleus. Some of it would become ionized and be swept away by the solar wind. Some would remain neutral and fluoresce under solar ultraviolet radiation. The dust would be propelled by radiation pressure, initiating the formation of a tail structure. Within hours to days, a visible coma would emerge. Within days to weeks, a developing tail would be apparent. There is no conceivable scenario where such a substantial mass loss could occur without generating an obvious visual signature. Unless, of course, the ejected material possesses properties radically different from our expectations. Perhaps the gas is expelling at a velocity far exceeding 300 meters per second, dispersing too rapidly to coalesce into a discernible coma. Alternatively, the dust grains might be exceptionally minuscule, submicron, or even nanometer in scale, rendering them effectively invisible to optical telescopes, immediately dispersed by radiation pressure or solar wind turbulence. It is also possible that the outgassing is occurring in highly collimated jets directed away from Earth, leading us to observe the nucleus but not the expelled material. Another possibility is that the surface is exceptionally reflective, or the dust exceedingly dark, such that the standard scattering and fluorescence mechanisms fail to operate as anticipated. These are all valid considerations, and we will explore them more thoroughly in due course. However, the uncomfortable reality is that each of these explanations necessitates the invocation of extraordinary circumstances, unusual conditions, or unconventional physics. In contrast, the most straightforward interpretation, one that requires no special pleading, is that 13% mass loss is simply not occurring. This implies that the non-gravitational acceleration is not being generated by conventional outgassing, meaning we are observing an object that does not conform to our models of cometary behavior. Some researchers have highlighted the importance of detection thresholds. While modern telescopes possess extraordinary sensitivity, they are not infinitely capable. Could the tail simply be too faint or too dispersed for us to detect? In principle, this is a possibility. However, we must be candid about the limitations of this argument. The telescopes observing 3 Atlas include some of the most powerful instruments ever developed by humanity. They are capable of detecting extremely faint emissions, mapping diffuse structures, and isolating signals from noisy backgrounds. If a substantial dust tail or gas envelope were present, these instruments would undoubtedly detect it. The fact that they are not detecting it is highly significant. You might be thinking to yourself, perhaps this celestial body is simply dormant. It could be an exhausted comet that long ago expended all its volatile materials and now possesses nothing more to offer. Such a supposition would indeed account for the lack of observable activity. However, it fails to explain the observed non-gravitational acceleration, which undeniably signifies the expulsion of material. Inactive comets do not exhibit acceleration that deviates from gravitational forces. They adhere strictly to predictable ballistic paths. 3 Atlas, however, is not conforming to this standard. Consequently, we find ourselves confronted with conflicting evidence. The motion patterns suggest activity, while the visual appearance indicates dormancy. Conventional comet physics cannot reconcile these two disparate observations. Either our comprehension is flawed, or this object possesses characteristics fundamentally distinct from the comets we have previously studied. This leads us to the pivotal question that will likely define the remainder of this investigation. What kind of entity exhibits such behavior? What visitor from beyond our solar system could display acceleration without any discernible loss of mass? Could it become brighter at specific wavelengths without forming a coma? Could it traverse its perihelion and solar storms without erupting into the spectacular display we have come to anticipate? Part 4. Initial Interpretations and Perspectives. The scientific community does not speak with a single voice regarding 3 Atlas, and that is precisely how it ought to be. What we are witnessing is the intricate, often contentious, yet self-correcting process of scientific inquiry, grappling with observations that defy established frameworks. Different researchers examine the identical data and arrive at divergent conclusions, each influenced by their specialized knowledge, their underlying assumptions, and their openness to considering unconventional explanations. Let us introduce some of the key voices in this discourse, as understanding the spectrum of interpretations will illuminate our path through the evidence. Stefan Burns, an observer who has meticulously tracked 3 Atlas, has emerged as a proponent of what we might term the radical reinterpretation faction. Burns contends that the absence of visible gas and dust release is not a matter of detection limitations or an issue of observation timing. Rather, it conveys fundamental information about the object's composition. If navigating perihelion and encountering solar storms failed to provide sufficient energy to initiate significant outgassing, then the conclusion appears unavoidable. It does not possess a high concentration of volatile compounds and dust to begin with. Burns has publicly declared his belief that 3 Atlas is, in fact, a solid mass of metal and carbon bearing no resemblance to an icy comet. This interpretation possesses the advantage of simplicity. It takes the observations at face value and posits, observe, if it does not behave like an icy comet, perhaps it is not an icy comet. It is possible we are dealing with an interstellar asteroid, a rocky or metallic body ejected from another star system that is coincidentally passing through ours. Such objects are theoretically expected to exist. Planetary formation is a tumultuous process, and collisions or gravitational interactions are bound to regularly propel rocky and metallic fragments into interstellar space. Eventually, some of these fragments will drift into other star systems. Indeed, it would be peculiar if we never encountered such entities. However, this interpretation must also account for the non-gravitational acceleration. This is where the situation becomes intricate. If the object is predominantly composed of metal and carbon with minimal volatile content, from whence does the acceleration originate? Burns and his colleagues in this camp might suggest that even a small quantity of volatiles, perhaps concentrated in isolated pockets beneath a resilient outer layer, could generate thrust without producing a visible coma. Alternatively, it is conceivable that the acceleration is not a product of outgassing at all, but rather stems from an entirely different mechanism that we have yet to fully comprehend. On the opposing side of this debate stands researchers such as Darrell Seligman, who has asserted that there is unambiguous evidence of cometary activity associated with 3 Atlas. Seligman's stance represents the more conservative viewpoint. This is indeed a comet displaying activity, and while its composition may be unusual, we should refrain from resorting to exotic explanations when standard comet physics can still potentially explain what we are observing. Perhaps the dust particles are exceptionally small, rendering the coma and tail more challenging to detect. Conceivably, the volatile content is less than that of typical solar system comets, yet still sufficient to drive activity. It is also possible that we are observing a comet that has undergone alterations over billions of years spent in interstellar space, its surface modified by cosmic rays and interstellar dust impacts to the point where it no longer behaves precisely like pristine cometary material. This perspective offers the benefit of conservatism. It does not necessitate the invention of new categories or the invocation of processes beyond our current understanding. Comets are inherently variable. They can surprise us. The very fact that 3 Atlas is an interstellar visitor implies that we should anticipate certain divergences from solar system comets, which originated within our specific protoplanetary disk and its unique compositional gradients. Different stellar systems may produce comets with varying volatile mixtures, distinct dust-to-ice ratios, and differing physical properties. Unusual does not necessarily equate to non-cometary. However, this interpretation must also explain the persistent elusiveness of evidence for activity. Why is a tail not visible? Why is the coma so faint or entirely absent in high-resolution imagery? The conservative contingent offers explanations: detection thresholds, viewing angles, peculiar grain characteristics. Yet these answers begin to accumulate into a list of special circumstances that prompts the question of whether we are exerting excessive effort to preserve the comet interpretation when perhaps we should be more amenable to exploring alternatives. Then there is Avi Lowe, the Harvard astrophysicist, who has become a somewhat contentious figure in recent years due to his willingness to entertain the possibility that certain astronomical anomalies might have artificial origins. Lowe views 3 Atlas through 2 primary lenses. Either it is an unusual comet, possessing characteristics we have not previously encountered, or it is a technological artifact, something manufactured by an intelligence, either functional or defunct, now adrift in interstellar space. Lowe does not claim to definitively know which interpretation is correct. He simply argues that, given the observed anomalies, we should be prepared to seriously investigate the technological hypothesis rather than dismissing it outright. This approach possesses the virtue of intellectual integrity concerning the limitations of our knowledge. We have observed a mere 3 confirmed interstellar objects: 1 IUAMU in 2017, 2I Borisov in 2019, and now 3I Atlas. This constitutes a sample size of 3. Drawing sweeping conclusions about the definitive nature of interstellar objects based on such a limited sample is epistemologically precarious. If we remain receptive to unexpected findings, we must at least consider possibilities that appear improbable based on our limited experience. And if we are indeed considering possibilities, the hypothesis of a technological artifact warrants consideration. Not due to its inherent likelihood, but because the repercussions of overlooking such a detection would be profound. However, this interpretation carries the immense burden of requiring extraordinary evidence to substantiate extraordinary claims. The mere strangeness of an object does not automatically imply artificiality. The universe is replete with strange phenomena arising from natural processes. If we are to seriously entertain the notion that 3 Atlas might be a manufactured object, we require more than just anomalies. We need affirmative evidence of artificiality: geometric structures, narrow-band radio emissions, materials with improbable natural abundances, something that cannot be explained by any plausible natural formation or alteration process. To date, we lack such irrefutable proof. What we are observing is as much a fascinating social phenomenon as a scientific one. The narrative surrounding 3 Atlas is evolving in real time, transitioning from that of merely another interstellar comet to something remarkably peculiar, with various factions staking out their positions across this spectrum. The media has capitalized on this tension, with some outlets publishing sensational headlines about alien probes, while others maintain a posture of skeptical caution. The public is understandably bewildered. Should we be excited? Should we be skeptical? Are astronomers withholding information, or are they exercising appropriate prudence? The significance of this debate extends beyond a single object. If 3 Atlas is simply an unusual comet, a natural body whose composition and behavior expand our understanding of cometary diversity, that in itself is scientifically valuable and intriguing. We would learn that interstellar comets can differ significantly from those in our solar system, offering insights into planetary formation conditions in other stellar systems. However, if it is something else entirely, whether a natural object belonging to a class we have not yet recognized or genuinely artificial, then the implications are vast. We would be confronted with evidence that our existing categories are inadequate, our assumptions are limited, and the cosmos harbors surprises we have yet to anticipate. And if one ventures into the realm of truly speculative thinking, we might be looking at the first detected piece of extraterrestrial technology, a discovery that would rank among the most significant in human history. One aspect appears certain. The debate is far from resolved, and further observations will be crucial to its eventual settlement. But for now, keep this range of interpretations in mind, because as we delve deeper into the data, you will witness how various pieces of evidence seem to bolster or undermine each camp's position. Part 5. Establishing the stakes. Before we embark on the technical deep dive promised in Act 2, it is imperative that we pause and consider what is truly at stake here. Why does it matter whether 3 Atlas is an unusual comet, a dense metallic and carbonaceous body, or something even more peculiar? What difference does the answer make to anyone beyond the small community of astronomers studying interstellar objects? The answer is that this is not merely an academic pursuit. The implications extend outward, impacting multiple domains of knowledge, from planetary science to astrobiology, and the search for intelligence beyond Earth. Furthermore, they touch upon fundamental questions regarding our position within a universe that we are only just beginning to comprehend. Let us commence with the most conservative scenario, the one that necessitates the fewest logical leaps. 3 Atlas is a natural object, but it represents a novel type of comet or a class of small body that we have not yet adequately categorized. Even this relatively modest conclusion would hold significant scientific weight. It would compel us to broaden our taxonomy, creating new classifications for both solar system and interstellar objects. Currently, we broadly categorize small bodies into comets, characterized by substantial volatile content and observable outgassing activity, and asteroids, which are predominantly rocky or metallic and exhibit no such activity. However, nature does not always adhere to our classifications. There exist objects that blur these distinctions, such as the main belt comets that orbit within the asteroid belt but occasionally display comet-like behavior. 3 Atlas may be revealing that the spectrum of small body types is more extensive than we previously believed, particularly when we include objects that formed in other stellar systems under differing conditions. This expansion of our taxonomic framework is important for our models of planet formation. When a protoplanetary disk collapses around a young star, the temperature gradient dictates where various materials can condense. In proximity to the star, temperatures are too high for volatile ices, resulting in the formation of rocky and metallic materials. Further out, beyond specific ice lines where different compounds can freeze, volatile-rich bodies begin to form. However, the precise details of this process, the exact temperatures, pressures, compositions, and timescales vary from system to system. By studying interstellar visitors, we are essentially sampling the products of planet formation in other stellar systems. Each visitor acts as a messenger, conveying information about conditions around other stars. If 3 Atlas informs us that certain systems produce an abundance of metallic and carbonaceous bodies, or that some comets can shed their volatiles through prolonged exposure to interstellar conditions, this constitutes valuable data regarding the diversity of planetary systems. The implications for astronomy extend even further. Our current understanding of cometary behavior is based almost exclusively on observations of solar system comets, objects that coalesced within our particular protoplanetary disk approximately 4.6 billion years ago. This is a biased sample. These comets share similar ages, formation conditions, and initial chemical compositions. Interstellar visitors break this bias. They originate from systems of varying ages, metallicities, and formation histories. By studying them, we can begin to ascertain which cometary properties are universal and which are merely incidental to the history of our specific system. Now, let us consider the implications for astrobiology, which may seem tangential until one recognizes that astrobiology ultimately seeks to understand the distribution of life-supporting conditions throughout the universe. The composition of small bodies is relevant to astrobiology because these objects deliver volatiles and organic compounds to planets. Earth's water likely originated in large part from cometary bombardment during and after the planet's formation. Many of the organic molecules that provided the fundamental building blocks for life may have been delivered via comets and asteroids. If we discover that interstellar objects possess significantly different compositions compared to solar system ones, perhaps richer in certain organic compounds, depleted in water, or carrying substances not found in local comets, this would provide insight into the chemical diversity of planetary systems and the range of initial conditions for potential biospheres. However, let us escalate to a more provocative scenario. What if 3 Atlas is not entirely natural? What if the artificial hypothesis proposed by Avi and a select few others holds even a kernel of truth? Suddenly, we are no longer discussing planetary science. We are engaging with the search for extraterrestrial intelligence, with technosignatures, with the possibility that humanity is not alone in the cosmos. This is where the stakes shift from merely scientific to existential. The search for extraterrestrial intelligence has traditionally focused on radio signals, operating under the assumption that a technological civilization might deliberately emit such signals. However, the exploration of interstellar objects offers an alternative avenue: the potential discovery of physical artifacts that might have been manufactured by other civilizations. If technological species are common in the galaxy, and if some of them develop interstellar travel or dispatch probes, then over billions of years, space should have accumulated a population of artificial objects, functioning probes, defunct machinery, debris from ancient spacecraft. A minuscule fraction of these objects might fortuitously pass through other star systems. Discovering one would be extraordinarily improbable, but not impossible. One IUMU, the first confirmed interstellar visitor in 2017, ignited precisely this kind of speculation. Its unusual elongated shape, its acceleration without visible outgassing, its tumbling rotation, all these features led some researchers to ponder its artificial origin. The majority of astronomers concluded it was likely natural, an unusual yet explainable product of some formation or alteration process we do not fully comprehend. However, the debate highlighted a crucial point. We do not currently possess clear criteria for distinguishing between artificial and natural objects at astronomical distances. If an interstellar probe or artifact were to traverse our solar system, would we even recognize it as artificial? What would its distinguishing signatures be? 3 Atlas presents similar questions, arguably in an even more acute form. If it exhibits acceleration without visible mass loss, possesses an unusual composition, and displays properties that do not fit neatly into natural categories, then these are precisely the kinds of anomalies one might expect from something manufactured. This does not automatically mean it is manufactured. Anomalies are not proof of artificiality, but they are potentially worthy of more rigorous investigation, employing multiple techniques and searching for the positive signatures that would differentiate the artificial from the natural. The sociological and cultural dimensions of this debate are also significant. How does the scientific community approach anomalies that might suggest the presence of intelligence? There exists a tension between maintaining appropriate skepticism and possessing the open-mindedness required not to overlook something extraordinary. There is also the matter of communication. How do scientists discuss these possibilities publicly without either sensationalizing them or reflexively dismissing them? The history of ufology has made many scientists hesitant to engage with anything that might be associated with aliens, even when the discussion is sober, evidence-based, and appropriately qualified. However, this historical baggage can potentially blind us to legitimate anomalies that warrant investigation. The window of opportunity here is brief and rapidly closing. 3 Atlas is receding from the Sun at approximately 33 kilometers per second. With each passing day, it moves farther away, becomes fainter, and is more challenging to observe. Eventually, within months to a couple of years, it will be too faint for even our most powerful telescopes to study in detail. It will then vanish back into interstellar space, and we will lose our chance to gather further data. This situation creates a sense of urgency. We have a limited time frame to direct our instruments at this object, to acquire spectra, to map its surface, and to search for any anomalies that might reveal its true nature. Once it has departed, we will be left with the data we managed to collect, and we will have to draw conclusions based on that finite data set. This urgency connects to a broader theme in contemporary astronomy. We are experiencing a golden age of discovery, a period where our instruments have finally become sophisticated enough to detect all manner of rare, peculiar, and unexpected phenomena. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, once operational, will identify thousands of small bodies each night, including additional interstellar visitors. We will be inundated with unusual objects, each potentially offering new insights into the cosmos. However, this abundance of data also necessitates improved frameworks for determining which anomalies warrant intensive follow-up investigation and which are likely merely routine variations. 3 Atlas is helping us develop these frameworks in real time. So, here is our current position. A single object traversing our solar system, stubbornly refusing to behave as anticipated. Multiple interpretations exist, each with its own distinct implications. A brief window of opportunity to gather data before it disappears forever. And a growing realization that our conclusions about this visitor might reshape our understanding not only of comets, but also of the types of objects that journey between the stars, and whether some of those objects might have been created by intelligent beings. In Act 2, we will meticulously examine every peculiar detail, every anomaly, every oddity that renders 3 Atlas so perplexing to explain. And you will discover the true depth of this enigmatic rabbit hole. Part 6, Cataloging the Anomalies. Let us systematically enumerate the peculiarities. What we are about to do is compile a comprehensive inventory of every unusual characteristic exhibited by 3 Atlas, comparing each one against the expected behavior of a typical comet or asteroid. By the conclusion of this exercise, you will grasp the reasons behind astronomers' profound bewilderment regarding this object. Each anomaly, when considered in isolation, might be explainable as a variation, a statistical fluke, or the consequence of unusual yet natural circumstances. However, When these anomalies are considered collectively, their cumulative impact becomes increasingly difficult to dismiss. This is the structure of a mystery, not a single definitive clue, but a constellation of oddities that, together, demand an explanation. Anomaly number 1, the orbit itself. 3 Atlas is traversing a retrograde trajectory, meaning it is orbiting the Sun in the opposite direction to the planets and most solar system objects. Orbits that proceed in the opposite direction of a system's primary rotation are not beyond the realm of possibility for natural celestial bodies. Some comets with extended orbital periods exhibit such trajectories. However, for an entity traversing the interstellar void, this retrograde motion is particularly noteworthy, as it profoundly influences our interpretation of its origins and its cosmic voyage. Even more striking is its orbital tilt in relation to the ecliptic plane, which is the nearly flat disk defined by Earth's orbital path, and is generally adhered to by all the planets. The orbit of 3I Atlas is inclined by approximately 5 degrees to the ecliptic. While this may not sound substantial, consider this. Celestial visitors from beyond our solar system arrive from random orientations in three-dimensional space. The likelihood of one appearing on a path so closely aligned with the plane of our solar system is approximately 0.2%, or 1 chance in 500. While not statistically impossible, it certainly raises eyebrows. One might posit that galactic dynamics could offer an explanation. Perhaps objects tend to congregate within the galactic disk, a region our solar system also inhabits. Consequently, approaches near the ecliptic might actually be more prevalent than pure random chance would suggest. This is a logical hypothesis and could account for some of the alignment, but it doesn't entirely resolve the peculiarity, especially when considered alongside other anomalies we are about to investigate. Keep this point in your mental tally as we proceed. Anomaly number 2 pertains to estimations of its size and mass derived from its brightness and assumed albedo, which refers to the reflectivity of its surface. Astronomers have calculated that the nucleus of 3I Atlas is considerably larger than previous interstellar visitors we have detected. One, designated I-2017 Oumuamua, was estimated to be a few hundred meters in length, possibly elongated but diminutive. 2, I-2019 Q4 Borisov, was approximately 1 kilometer in diameter, a size fairly typical for a cometary nucleus. 3I Atlas, depending on assumptions regarding its albedo and shape, could be several kilometers across. If it comprises a dense metallic and carbonaceous composition, as some researchers propose, its mass could be substantial, potentially orders of magnitude greater than that of Oumuamua or Borisov. The significance of this lies in the fact that larger celestial bodies are inherently rarer. The distribution of sizes for smaller bodies follows a power law. Numerous small objects exist, with progressively fewer larger ones. If 3I Atlas is genuinely large, its presence as a random visitor becomes statistically less probable, though not impossible. Furthermore, it impacts our understanding of the lack of observable outgassing. A larger object with greater thermal inertia might manage its internal heat differently, possess a thicker, processed surface layer, and react distinctively under solar heating compared to a smaller entity. Anomaly number 3 concerns its compositional signatures, and this is where the situation becomes truly perplexing. Observations have indicated emissions from 3I Atlas that suggest the presence of nickel within the released gas. While nickel itself is not entirely absent from comets, metallic elements can be found as minor constituents in cometary dust and can be expelled during heating. The proportion of nickel relative to other elements appears anomalous. Specifically, claims suggest that the nickel-to-cyanide ratio is significantly higher than what is typically observed in comets. Concurrently, water, which should be the predominant volatile in any conventional comet, seems to be severely depleted. Some reports indicate a water content of around 4% by mass, a stark contrast to the 50% or more expected in a typical icy comet. It is crucial to acknowledge the inherent uncertainty here. These compositional measurements are challenging to perform accurately, and not all of them have undergone comprehensive peer review and confirmation. Assertions regarding specific compounds, such as nickel tetracarbonyl, a highly toxic industrial chemical, have surfaced in some media reports, but should be approached with caution until rigorously validated through precise spectroscopic analysis. Nevertheless, even if we adopt a more conservative stance and simply accept the presence of nickel emissions and the depletion of water, this combination is difficult to reconcile with conventional cometary models. Where did this object originate, such that nickel is abundant and water is scarce? What process could yield such a composition? Anomaly number 4 relates to its polarization characteristics. When light interacts with particles and scatters, it can become polarized, meaning its electromagnetic waves oscillate preferentially in certain directions rather than randomly. By measuring the polarization of sunlight reflected from an object, astronomers can glean information about the size, shape, and composition of the scattering particles. 3I Atlas reportedly exhibits extreme negative polarization, indicating that the scattered light is polarized perpendicular to the expected orientation. This behavior is unlike known comets, which typically display positive polarization resulting from dust scattering. Such pronounced negative polarization suggests either highly unusual particle properties, perhaps highly metallic grains or significantly irregular shapes, or a combination of factors not commonly encountered. Again, we must exercise caution regarding definitive conclusions. Polarization measurements are technically demanding and are influenced by observing conditions. However, if this finding is substantiated, it points towards a surface or surrounding particle cloud possessing characteristics that deviate from typical cometary dust. Anomaly number 5 is the rapid brightening and color alteration observed as it approached perihelion. As 3I Atlas neared the Sun, its brightness increased dramatically, a five-fold surge in green band flux, as previously mentioned. However, the pattern of brightening and the associated color shift were unusual. The object appeared to exhibit a bluer hue near perihelion, potentially signaling alterations in its surface properties or the emergence of different emission mechanisms. For a standard comet, increased brightness near perihelion is attributed to enhanced dust production and gas fluorescence, and one would anticipate specific color trends based on dust grain characteristics and gas chemistry. The behavior of 3I Atlas does not quite align with these expectations, suggesting either atypical changes in surface albedo or emissions from constituents not typically dominant in comets. Anomaly number 6 brings us back to the central paradox: non-gravitational acceleration without corresponding visible ejecta. We have already discussed this, but it merits inclusion in this catalog as it is arguably the most perplexing aspect. The measured acceleration is demonstrably real and significant. The absence of a visible coma and tail is equally factual. Reconciling these two facts necessitates invoking either exceptionally high gas ejection velocities, extremely fine and thus invisible dust, undetected narrow jets, or some entirely different phenomenon. None of these potential explanations is independently satisfactory. Now, let us consider the probabilities. Each anomaly possesses some probability of occurring naturally. A retrograde orbit aligned with the ecliptic has a 0.2% chance. An unusual composition with high nickel and low water is difficult to quantify precisely, but is certainly uncommon based on our sample of comets. Extreme negative polarization is rare. Acceleration without visible outgassing is very rare. When independent, unlikely events are combined, their probabilities are multiplied. If each anomaly has a 10% chance of occurring naturally, which is likely a generous estimation, and we consider 5 independent anomalies, the probability of all 5 occurring simultaneously by chance is 0.1 raised to the 5th power, which equals 0.001%, or 1 chance in 100,000. Of course, these anomalies might not be independent. It is possible they are all manifestations of a single underlying characteristic. For instance, if the object is metal-rich, this could account for its composition, polarization, lack of a tail, and unusual thermal response simultaneously. In such a scenario, we should not multiply the probabilities because they are interconnected. Nevertheless, the question remains, why is this object metal-rich? How prevalent are metal-rich interstellar bodies? Are we simply fortunate to have encountered one, or is there another explanation at play? The issue of data reliability looms over all these considerations. Not every purported anomaly carries equal weight of evidence. Some measurements originate from instruments with robust calibration and well-established methodologies. The orbital parameters from JPL, for example, are exceptionally precise. Other measurements are more provisional. Compositional assertions derived from spectroscopy can be influenced by assumptions regarding temperature, viewing geometry, and signal-to-noise ratios. As we discuss these anomalies, it is essential to maintain a hierarchical understanding of confidence. What we can state with certainty is that 3I Atlas is unusual. The precise degree of its unusualness and the specific ways in which it deviates are still being determined. Here is a useful thought experiment. Imagine you are tasked with designing an interstellar object from scratch, aiming to make it as peculiar as possible while still potentially appearing natural. You would likely equip it with an unconventional orbit, a peculiar composition, anomalous acceleration, and minimal visible activity. You would ensure it is large enough to be detectable, but small enough to remain enigmatic. You would incorporate just enough anomalies to puzzle scientists without overtly suggesting artificiality. 3I Atlas aligns with almost every aspect of this hypothetical design, which is either a remarkable coincidence or an indication that something fundamental about our classification systems is flawed. As we move forward, the central question becomes, how do we account for this collection of peculiarities? Is there a unifying model, whether natural or otherwise, that can explain everything we observe? Or are we compelled to accept that some features remain genuinely enigmatic, at least until further data is acquired? Part 7 delves into compositional and physical models. We must engage with concrete physical models now, as vague speculation will not suffice. If 3I Atlas possesses the metal and carbon-rich composition that the evidence suggests, we must understand its physical implications, how such an object could form, and what observable consequences it would entail. Let us begin by contrasting the properties of refractory materials with volatile ices, as this distinction is fundamental to comprehending why a metal-rich body would behave so differently from an icy comet. Refractory materials, such as metals like iron and nickel, rocky silicates, and carbon compounds like graphite, are substances that remain solid at extremely high temperatures. When subjected to solar radiation, they do not readily sublimate, unlike water ice or frozen carbon dioxide. Instead, they conduct heat into their interior, gradually warm up, and can reach elevated temperatures without significant mass loss through vaporization. This results in markedly different thermal behavior. An icy comet responds to solar heating by sublimating volatiles, which carries heat away through the latent heat of phase transition. A metal-rich object, conversely, absorbs heat, and its temperature rises until thermal radiation dissipates the energy. The equilibrium temperature might actually be higher for the refractory object due to the absence of evaporative cooling. If 3I Atlas has a predominantly metal and carbon composition, this would immediately explain the lack of a visible tail. There is no dust to form a tail because very little volatile ice is sublimating to carry dust particles away from the surface. Any dust present is presumably embedded within the solid matrix and is only released if surface material is physically disrupted, perhaps by micrometeorite impacts or thermal stresses. The observed brightening might stem from the exposure of fresh, more reflective material as the surface erodes, or from changes in surface temperature influencing infrared thermal emission. But where would such an object originate? What natural processes can produce metal-rich bodies in interstellar space? One plausible explanation is that 3I Atlas is a fragment originating from a differentiated body, such as a small planet or a large asteroid that underwent internal melting, leading to separation into a metallic core and a rocky mantle. A catastrophic collision could shatter such a body, ejecting fragments into space. Some of these fragments would consist of core material, predominantly metal. Over time, processing by cosmic rays and space weathering could alter the surface, potentially depositing carbonaceous compounds. Eventually, gravitational interactions with planets or close stellar passages could impart sufficient velocity for the fragment to escape its home star system entirely. Billions of years later, it wanders into our solar system, a relic of violent events in a long-ago planetary system. This natural formation scenario is conceivable. We know that differentiation occurs. We are aware that catastrophic collisions happen. We understand that bodies can be ejected into interstellar space. This model does not necessitate any exotic physics or unknown processes. It is conservative and aligns with our understanding of planetary system evolution. The primary question is statistical. How common are such objects? If metal-rich interstellar fragments are rare, then detecting one among our limited sample of 3 interstellar visitors could be a matter of luck. If they are common, then our solar system's cometary population is skewed and unrepresentative, which would be an interesting finding in itself. Now, let us consider an alternative hypothesis that causes discomfort for many scientists, but persistently remains a possibility. The notion that 3I Atlas is not entirely natural, but rather represents a manufactured object, or at least something that has been modified by processes not typically associated with natural astrophysical evolution. Before your skepticism detectors go into overdrive, and they should, as extraordinary claims demand extraordinary evidence, let us examine what this hypothesis entails and what observational signatures it might predict. An artificial object engineered for interstellar travel would likely prioritize certain design features: low mass for easier acceleration, a high strength-to-weight ratio, and potentially a reflective surface to harness radiation pressure. It would also feature minimal volatile content, as volatiles add mass without providing structural benefits. If you were designing an interstellar probe or sail, you might construct it from lightweight metals, carbon composites, or thin films, deliberately avoiding water ice and other volatiles unless they served a specific purpose. The resulting object would be dense, refractory, and would exhibit minimal outgassing even when heated. Does this description sound familiar? It should, because it largely characterizes 3I Atlas: the lack of water, the presence of metals, and the absence of a dust tail. All these characteristics are consistent with what one might expect from a manufactured object rather than a natural comet. The observed non-gravitational acceleration could arise from the deliberate venting of stored propellant through narrow jets, from radiation pressure acting on a large surface area, or from some mechanism we have yet to identify. The unusual orbit could be the result of deliberate navigational choices made long ago, though this line of reasoning quickly enters speculative territory. However, the crucial point is this. Superficial similarity to a hypothetical artificial object does not constitute evidence of artificiality. It merely indicates consistency. To genuinely support the artificial hypothesis, we would require positive evidence that cannot be explained by natural phenomena. For instance, if we detected structured radio emissions modulated in a manner inconsistent with natural occurrences, that would be strong evidence. If we observed geometric shapes, perfect spheres, cylinders, regular polygons, that would be suggestive. If spectroscopic analysis revealed materials with isotopic ratios impossible in nature or alloys requiring smelting, that would be compelling. If we detected energy sources incongruous with solar heating and radioactive decay, we would have to seriously consider artificiality. We possess none of that. What we have is an object with anomalous properties that do not fit comfortably within existing natural categories. This warrants further investigation, the deployment of additional instruments, and the application of multiple diagnostic techniques, but it does not prove anything beyond the possibility that our existing categories may require expansion. There is also an intermediate possibility worth considering. Perhaps 3I Atlas is natural, but has been significantly altered by its prolonged journey through interstellar space. A recent study has proposed that bombardment by cosmic rays over billions of years can modify ice structures down to depths of 15 to 20 meters. High-energy particles strike the surface, breaking molecular bonds, rearranging crystal structures, and creating new compounds through radiolysis. Over immense timescales, this processing could transform the outer layers of an icy body into something quite different. It might form a refractory crust that seals volatiles beneath, or a chemically altered regolith with properties unlike anything observed in solar system bodies that have not undergone such prolonged exposure. This cosmic weathering hypothesis is appealing because it bridges the natural and the anomalous. It posits that the object began as a conventional comet, but was transformed into something unusual by billions of years of interstellar exposure. The alteration itself is natural, as cosmic rays are a known phenomenon, but the timescales involved are considerably longer than what solar system bodies typically experience. This could explain why 3I Atlas appears different from 2I Borisov, which might have been ejected more recently and thus not undergone as much processing. The observations from the James Webb Space Telescope on August 6th, utilizing near-infrared spectrograph, NIR-SPEC, should be particularly informative. Near-infrared spectroscopy can reveal the chemical composition of surface materials and any gas being released. If the spectra indicate the presence of typical cometary molecules, water, carbon monoxide, carbon dioxide, simple organic compounds, then the cosmic weathering model gains support. Conversely, if we detect exotic compounds or anomalous abundance ratios that cannot be produced through known radiolysis processes, this would push us toward more unconventional explanations. One aspect that merits attention is the absence of observed dust despite significant solar heating. If 3I Atlas possesses a metal-rich surface, it might simply not be producing dust because there is no dust to produce. Alternatively, its surface might be sealed by a fusion crust, not literal fusion in the sense of high-temperature melting, but rather a consolidated layer formed by micrometeorite impacts and radiation processing that binds surface particles into a coherent shell. Such a crust could insulate subsurface volatiles, preventing their escape even when subjected to heat. Eventually, thermal stresses might fracture the crust, leading to sudden outbursts, but between these events, the object would appear inactive. The challenge for any proposed model is to simultaneously explain all the observations. The natural metal-rich fragment model accounts for the composition and lack of a tail, but struggles to explain the acceleration. The cosmic weathering model explains surface properties but requires reconciliation with the reported anomalous composition. The artificial hypothesis aligns with multiple features but lacks direct evidence and involves extraordinary assumptions. No model is perfect, implying either that we are missing data, misinterpreting existing data, or that the object genuinely represents something beyond our current frameworks. What we can state with confidence is that 3I Atlas is compelling us to reevaluate what interstellar objects can be, how they form, how they evolve, and how we should classify them. This intellectual exercise is valuable regardless of which model ultimately proves correct. Part 8 focuses on the mechanism of acceleration and the absence of a tail. The paradox of acceleration deserves its own focused examination, as it lies at the core of this mystery. Let us proceed quantitatively and detail precisely what the measured non-gravitational acceleration signifies, what it implies about mass loss, and why the numerical data contradicts the visual evidence. This is where the discrepancy between the object's motion and its appearance becomes mathematically pronounced. The measured acceleration comprises two components, radial and transverse. The radial component, representing acceleration along the line connecting the object to the Sun, is approximately 1.1 times 10 to the power of -6 astronomical units per day squared. The sidewise acceleration, the force perpendicular to that trajectory, registers at approximately 3.7 times 10 to the -7th power astronomical units per day squared. These figures may appear abstract, so let us reframe them using more familiar metrics. 1 astronomical unit per day squared equates to roughly 169 meters per second squared. Consequently, the radial acceleration is about 0.00186 meters per second squared. This is exceedingly minute, approximately 20,000 times less potent than Earth's gravitational pull at its surface. Nevertheless, it is demonstrably real, measurable, and necessitates a coherent explanation. For conventional comets, acceleration not attributable to gravity stems from a propulsion effect. Gases sublimate from the surface, accelerate outwards, and in doing so, impart a reactive force upon the nucleus. This is a direct manifestation of Newton's third law. The magnitude of this force is contingent upon the velocity of the escaping gas and the rate at which mass is expelled. For the gases sublimating from water ice on comets, typical exit velocities range from 300 to 1,000 meters per second, influenced by temperature and the geometric configuration of the outgassing. We will adopt 300 meters per second as a conservative estimate. With this, we can proceed with calculations. If one knows the acceleration and the ejection velocity, it is possible to reverse engineer the necessary mass loss rate to achieve that acceleration. The governing equation is straightforward. Acceleration equals the mass loss rate multiplied by the ejection velocity, divided by the object's total mass. Rearranging this yields mass loss rate equals acceleration multiplied by mass, divided by ejection velocity. Plugging in our values, assuming a mass derived from size and density estimations, we arrive at a mass loss rate that, when integrated over the observation period from perihelion through early November, accounts for roughly 13% of the object's total mass. 13%. Let that register. If 3 Atlas shed 13% of its mass through gas expulsion over a mere few weeks, that is not subtle activity. That represents vigorous outgassing comparable to highly active comets when they are in close proximity to the Sun. The released gas alone would generate a substantial coma. The dust carried within that gas, even if it constitutes a minor fraction of the gas mass, would scatter sunlight, thereby creating observable structures. It would be impossible to conceal such a significant mass loss. Yet, we are not observing it. The images from November 5th depict a point source resembling a star. High-resolution observations reveal a minimal coma, no discernible tail structures, and the dust and gaseous envelope that should be present, the entire visible signature of active mass expulsion, is either absent or significantly fainter than preliminary calculations would suggest. Therefore, an assumption within our calculations must be erroneous. Let us scrutinize these assumptions. Firstly, the ejection velocity. It is conceivable that the gas is not traveling at 300 meters per second. Perhaps it is moving considerably faster. If the ejection velocity were 10 times greater at 3,000 meters per second, then only 1/10 the amount of mass loss would be required to produce the same acceleration, reducing the projected mass loss from 13% to approximately 1.3%. While still substantial, this is more readily concealed. However, how could gas achieve a velocity of 3,000 meters per second? This speed approaches the escape velocity of Mars. For gas to attain such velocity, it would either need to possess extreme temperatures in the thousands of Kelvin or be accelerated by forces other than thermal pressure. Neither of these scenarios aligns comfortably with our current understanding of cometary physics. Our second assumption concerns the dust-to-gas ratio. It is possible that this ratio is exceptionally low. Typical comets expel a composite mixture of gas and dust, with dust frequently comprising a significant portion of the ejected mass. It is this dust that forms the visible tail. If 3 Atlas is expelling primarily gas with very little dust, the coma and tail would be considerably fainter and more challenging to detect. But why would the dust-to-gas ratio diverge so greatly from that of typical comets? Potentially due to compositional differences, if the object is metal-rich with scarce friable material, meaning there is simply insufficient dust to eject. Alternatively, the dust particles might be exceedingly small, submicron in size, which are rapidly dispersed by radiation pressure and dissipate too quickly to form a coherent structure. Smaller particles are also less effective at scattering light, rendering them more difficult to detect. Our third scenario posits that the gas is being expelled in highly focused jets rather than diffuse plumes. If outgassing occurs through narrow fissures or vents, generating beam-like jets instead of broad sprays, then the majority of the gas and dust might be ejected in directions other than towards Earth. We would observe the nucleus, but not the ejected material. Some comets do exhibit focused jets, visible in high-resolution imagery, as narrow streaks emanating from the nucleus. However, even these focused jets eventually disperse and form a wider coma at greater distances. Concealing all ejected material solely through jet geometry presents a significant challenge. Our fourth possibility relates to radiation pressure or solar sail effects. If 3 Atlas possesses a very low mass relative to its size, perhaps it is a thin membrane or has a highly porous structure, then radiation pressure from sunlight could induce acceleration without any mass expulsion whatsoever. Photons carry momentum, and upon reflecting off a surface, they impart a force. For most comets and asteroids, this force is insignificant compared to their mass. However, for an object with a sufficiently low mass and a large cross-sectional area, radiation pressure becomes a considerable factor. This was one of the hypotheses proposed for Oumuamua's acceleration. The challenge here is that achieving the requisite mass-to-area ratio necessitates either implausibly low densities or impractically large surface areas. A solid metallic object would not fulfill these conditions. One would require something akin to a vast, thin sail. Our fifth option, venturing into more speculative realms, suggests that the acceleration might not originate from natural processes at all. If 3 Atlas were artificial, equipped with internal mechanisms for generating thrust, the acceleration could be derived from controlled venting of stored propellant, a form of photon drive, electromagnetic interactions with the solar wind, or through mechanisms yet unimagined. The crucial point is that artificial systems can generate thrust without producing visible plumes. A contemporary spacecraft employing electric propulsion, for instance, exhibits nearly invisible exhaust. An ion drive expels particles at such high velocities and in such minuscule quantities that its exhaust plume is effectively transparent. I wish to be unequivocally clear. Invoking artificial mechanisms is not a step to be taken lightly. It is an explanation of last resort, to be considered only after all natural possibilities have been thoroughly exhausted. However, intellectual integrity compels us to acknowledge that if we are genuinely perplexed by the acceleration mechanism, and if no natural explanations fit comfortably, then we should not categorically dismiss alternatives simply because they are uncomfortable or improbable. Scientific progress is predicated on the exploration of all possibilities and the meticulous weighing of evidence, not on the imposition of ideological boundaries around acceptable hypotheses. Part 10. Observational timing, solar context, and environment. The timing of our observations is of paramount importance. To comprehend why 3 Atlas presents such a puzzle, we must examine the environmental context of its passage through the inner solar system. This extends beyond mere location or temperature. It encompasses the entire ecosystem of radiation, particles, and forces that should have instigated activity if this were a typical comet rich in volatiles. The fact that we did not observe such activity, despite ideal triggering conditions, deepens the mystery. Let us establish the precise setting. 3 Atlas reached its perihelion on October 29, 2025, at a distance of approximately 1.38 astronomical units from the Sun. This equates to roughly 128 million miles, positioning it comfortably between Earth's orbit at 1 astronomical unit and Mars' orbit at 1.5 astronomical units. For context, this distance falls well within what astronomers term the water-ice sublimation zone. At this range, solar heating is sufficient to vaporize water ice from a comet's surface at a considerable rate. We are not discussing extreme proximity, such as with sun-grazing comets that plunge within a few solar radii and are utterly incinerated. This represents a relatively gentle heating environment where typical cometary activity should proceed steadily and predictably. The thermal input at 1.38 astronomical units is substantial. The solar constant at Earth's distance is approximately 1,360 watts per square meter. At 3 Atlas's perihelion distance, it receives roughly 700 watts per square meter of solar radiation. This is akin to directing multiple heat lamps onto every square meter of the object's sunlit surface, hour after hour, day after day. Any water ice exposed to this flux will sublimate. Carbon dioxide ice, which vaporizes at even lower temperatures than water, should be vigorously expelled. Frozen carbon monoxide, ammonia, methane, all the usual cometary volatiles, should transition from solid to gas and escape into space. However, solar heating is only one facet of the environmental narrative. The sun is not a static heat source. It is a dynamic, volatile plasma sphere that regularly unleashes solar storms, coronal mass ejections, and energetic particle events. During the period surrounding 3 Atlas's perihelion passage, the Sun was exhibiting heightened activity. Solar storms propagate shock waves of charged particles outward through the solar system at speeds of hundreds to thousands of kilometers per second. These particles carry energy. Upon impacting a cometary surface, they can further heat it, sputter material from the surface, charge dust grains, and generally intensify activity. The solar wind itself, a continuous stream of protons and electrons flowing from the Sun at all times, intensifies closer to the Sun. At one point, 3/8 astronomical units, 3 Atlas, was enveloped in a solar wind of sufficient density and velocity to interact robustly with any outgassing. The solar wind ionizes gas, stripping electrons from molecules and creating the glowing ion tail characteristic of active comets. It also exerts pressure on cometary material, contributing to the shaping and extension of tails. The confluence of thermal input, particle bombardment, and electromagnetic interactions should have fostered ideal conditions for cometary activity. Yet, we observed virtually nothing. The images from November 5th, captured 1 week post-perihelion, reveal a star-like point. This timing is significant because cometary activity does not cease instantaneously upon an object's perihelion passage. The nucleus retains heat. Subsurface ice continues to sublimate. Jets persist in their expulsion. Activity typically remains elevated for days to weeks after perihelion before gradually diminishing as the comet recedes and cools. We should have been observing 3 Atlas during its peak activity phase when any present volatiles would still be enthusiastically venting. So, what could account for the absence of visible activity despite these favorable conditions? One possibility involves the concept of a refractory crust or mantle. Comets can develop an insulating layer on their surfaces over time. If the nucleus has been traversing interstellar space for millions or billions of years, its surface may have undergone alterations due to cosmic ray exposure, forming a hardened shell. Recent research has investigated precisely this scenario for 3 Atlas. A study published in 2025 explored how cosmic rays, high-energy particles pervasive throughout the galaxy, would impact an icy body during an extended interstellar journey. The findings were revealing. Cosmic rays penetrate cometary ice, disrupting molecular bonds and triggering chemical reactions. Over millions of years, this process can alter the ice down to depths of 15 to 20 meters, creating what is essentially a processed, compacted layer, quite distinct from pristine ice. This cosmically gardened material might be less porous, less susceptible to rapid sublimation, and generally more refractory than fresh cometary ice. If 3 Atlas possesses such a layer, it could function as an insulating blanket, trapping volatiles beneath and allowing only minimal outgassing, even under intense solar heating. But does this fully explain our observations? An insulating crust might retard or diminish activity. However, if significant volatiles lie beneath, eventually that crust should fracture. Thermal stresses, pressure buildup from subsurface sublimation, and the sheer intensity of perihelion heating should cause the surface to crack in places, permitting gas to escape through vents or jets. We observe this phenomenon in solar system comets that develop crusty mantles. They do not entirely suppress activity, they merely render it more episodic and localized. 3 Atlas appears to be suppressing activity far more effectively than a simple crust model would predict. Another environmental consideration is solar proximity and the history of heating. If 3 Atlas had previously passed in close proximity to another star during its interstellar journey, perhaps its home star billions of years ago, or encountered another star en route, it might have already shed its most volatile surface materials. The object we are observing now could be thermally processed, with only deeply situated or refractory volatiles remaining. These deep volatiles might be venting slowly, generating the measured acceleration without producing a visible coma because the mass loss rate is too low to accumulate a substantial dust and gas cloud. Viewing geometry also plays a role, although this explanation has limitations. Perhaps the outgassing jets are highly directional, pointing away from Earth or along our line of sight, thus obscuring the resultant coma and tail structure. It is possible that the dust is being ejected at angles that render it invisible to our telescopes. However, this necessitates a rather contrived geometry and does not account for the complete absence of any diffuse glow surrounding the nucleus in high-resolution images. Solar conjunction presents another timing challenge. During specific orbital phases, the object might have been too close to the Sun in the sky for ground-based telescopes to observe effectively, being blinded by solar glare. Early observations might have missed crucial episodes of activity. Nevertheless, space-based telescopes, such as Hubble and James Webb, do not face the same constraints and have been monitoring this object through multiple observation windows. The fact that they too report minimal activity suggests that it is not solely an issue of observational timing. There is also the possibility that solar storms did not enhance activity, but rather suppressed it or eradicated evidence of it. This might seem counterintuitive, but bear with me. If 3 Atlas was generating a very tenuous dust envelope, barely sufficient for detection, intense solar storm particle fluxes might have swept that dust away more rapidly than usual, preventing the accumulation of a visible coma. Alternatively, the storms could have charged the dust grains so strongly that electrostatic repulsion dispersed them quickly, again hindering buildup. This is speculative, but it illustrates that the solar environment is complex, and interactions may not always yield simple, predictable outcomes. The material properties of a metal and carbon-rich body respond differently to solar heating compared to icy bodies. Metals possess high thermal conductivity. They readily absorb heat, but also conduct it into their interior rather than concentrating it at the surface where sublimation occurs. A metallic surface could reach high temperatures without necessarily inducing rapid venting of trapped subsurface volatiles. Metals also exhibit high reflectivity at certain wavelengths. If the surface is highly reflective, perhaps metallic nickel or iron reflecting sunlight, it might absorb less thermal energy than a dark cometary surface would. This could reduce heating efficiency and slow sublimation rates. Carbon-rich materials offer another perspective. Comets contain carbonaceous compounds. However, if 3 Atlas is unusually dominated by carbon, perhaps resembling carbonaceous chondrite meteorites or even graphite in places, its thermal characteristics would be significantly different from typical ice dust mixtures. Carbon possesses high thermal stability. It does not sublimate at temperatures relevant to the inner solar system. A carbon-rich object might simply absorb solar heat and re-radiate it into space without producing significant outgassing. All these environmental and material considerations converge on a single conclusion. 3 Atlas is not reacting to its environment in the manner expected of a typical comet rich in volatiles. Whether this is due to prolonged processing during interstellar transit, an unusual bulk composition, protective surface layers, or a combination of factors, the object appears resistant to the standard triggers that would produce spectacular cometary activity. And it is precisely this resistance that renders it so fascinating and so challenging to categorize. In the subsequent section, we will explore how the scientific community and broader culture are confronting this anomaly and the often uncomfortable tensions that arise when observations deviate from expectations. Part 10: Controversies, Institutional Responses, and Conspiracies. Science does not operate in isolation, and the narrative of 3 Atlas is as much about how institutions, researchers, and the public react to anomalies as it is about the anomalies themselves. There is a compelling sociology to this mystery, a drama unfolding across academic papers, press releases, social media discussions, and informal conversations among astronomers. Understanding these dynamics is crucial for appreciating why certain interpretations gain traction while others are dismissed, and why the process of making sense of peculiar observations can be slower and more complex than we might anticipate. The scientific establishment, including NASA, the European Space Agency, major universities, and professional astronomy organizations, operates under principles of caution and peer review. This is generally a strength, preventing premature announcements, filtering out observational errors and hasty interpretations, and maintaining credibility by ensuring claims are well substantiated before widespread dissemination. However, it also engenders institutional inertia. Organizations are averse to risk, particularly when extraordinary claims are involved. To suggest, even tentatively, that an astronomical object might be artificial carries immense reputational risk. If one errs, they risk becoming known as the individual who claimed an alien probe and wasted everyone's time. If they are correct, it seems almost impossible, so why incur the risk? This creates an asymmetric incentive structure. There is minimal upside and substantial downside for a major institution to be the first to propose that 3 Atlas might be artificial. It is far safer to adhere to conventional explanations, emphasizing the need for more data and suggesting the object is unusual but likely natural. And frankly, this is probably the correct stance most of the time. Anomalies typically resolve into prosaic explanations once they are better understood. The history of astronomy is replete with mysteries that dissolved under scrutiny. Pulsars, initially thought to be alien beacons, now understood as rotating neutron stars. Fast radio bursts, once inexplicable, now recognized as natural cosmic phenomena. However, this caution can sometimes morph into excessive conservatism, a reluctance to seriously investigate possibilities that seem improbable but not impossible. We witnessed this tension manifest dramatically with Oumuamua. When that object displayed non-gravitational acceleration and an unusually elongated shape, Avi Loeb raised the question of whether it might be artificial, specifically suggesting it could be a light sail, a large, thin sheet propelled by starlight. Most astronomers dismissed this hypothesis, arguing that natural explanations were more plausible. A cometary outgassing explanation was eventually developed and gained acceptance, though not without some lingering questions. 3 Atlas has reignited similar debates, but with arguably more compelling evidence. The combination of acceleration without visible outgassing, unusual composition, and several other anomalies makes the natural explanations less comfortable than they were for Oumuamua. This has resulted in a fragmented landscape of opinion. Several academics openly posit the notion that this celestial body might elude all natural classifications currently understood. Conversely, others adamantly uphold conventional interpretations of comets, asserting that we are merely observing typical variability magnified by insufficient data. A select few, however, voice publicly what many contemplate privately, that we ought to thoroughly examine the possibility of this object being artificial. The media's involvement in this narrative is multifaceted. Science journalism navigates a delicate balance, striving to accurately convey uncertainty while simultaneously offering readers concrete points of reference. Headlines proclaiming alien probes or enigmatic interstellar visitors capture attention and foster engagement. Nevertheless, they also carry the risk of misrepresenting the current evidentiary status to the public. Some media outlets have embraced sensationalism, featuring stories that strongly suggest Three-Eye Atlas could be artificial, while downplaying the numerous disclaimers and uncertainties involved. Other publications have adopted a more reserved approach, presenting observed anomalies yet emphasizing that natural explanations remain viable. This divergence creates confusion for an interested populace. For individuals not deeply entrenched in the astronomical community, discerning well-supported claims from speculative ones proves challenging. Are the detected nickel emissions genuine? Are they as anomalous as some reports suggest? The reality is that some of the most striking assertions about Three-Eye Atlas have yet to undergo comprehensive peer review. Reports of nickel tetracarbonyl, that volatile nickel compound previously mentioned, appearing in publications like Newsweek and the New York Post, are circulating. These are not scholarly journals. They are reporting on preliminary observations or unofficial statements that have not been subjected to the rigorous scrutiny of peer review. This situation illuminates a significant issue in contemporary scientific communication. The traditional scientific progression, making an observation, analyzing data, writing a manuscript, submitting it for peer review, awaiting months for revisions and publication, and then announcing the findings, is proving too slow for the digital age. By the time a paper is officially published, the subject has already been widely discussed, analyzed, and debated across social media platforms and popular science outlets. Researchers often feel compelled to comment publicly on ongoing work, leading to a surge of preliminary findings that may not withstand closer examination. We must also address speculative interpretations that border on conspiracy theories, as they exist and influence public perception of this object. Certain online communities have seized upon Three-Eye Atlas as evidence of government cover-ups, hidden alien contact, or other conspiratorial narratives. These interpretations typically hinge on the presumption that authorities possess more information than they reveal, and that definitive proof of artificiality is being deliberately withheld from the public. This is almost certainly not the case. The astronomical community is vast, international, and highly competitive. If irrefutable evidence existed suggesting Three-Eye Atlas was artificial, it would be exceedingly difficult to conceal. Someone would undoubtedly publish, leak the information, or seek recognition for what would be the most significant discovery of the century. The more prosaic reality is that we simply do not know yet. We are faced with anomalies that lack clear explanations. We have competing hypotheses, none of which perfectly align with all the available data. Institutional caution is at odds with the willingness of individual researchers to speculate. Furthermore, we have a limited time frame to gather additional observations before the object becomes too faint for effective study. This situation engenders frustration across all parties. Researchers are frustrated by restricted telescope access and incomplete data. Institutions feel pressure to issue pronouncements before conclusive evidence emerges, and the public is frustrated by science's apparent inability to provide a straightforward answer. There is also an ethical consideration regarding how we communicate about such objects. If we prematurely leap to conclusions about potential artificiality, we risk raising false alarms, thereby diminishing public trust in astronomical announcements. When the next truly extraordinary discovery surfaces, will it be believed? Conversely, if we are overly dismissive of anomalies, too hasty in forcing observations into established categories, we might overlook something genuinely groundbreaking. Achieving the right balance, combining open-minded skepticism, rigorous investigation, and honest communication about uncertainty, is considerably easier said than done. The issue of resource allocation is also pertinent. Telescope time is a precious and oversubscribed commodity. Every hour dedicated to observing 3I Atlas means not being used for other scientific endeavors, such as characterizing exoplanets, surveying distant galaxies, or tracking near-Earth asteroids, all research activities that compete for the same instruments. This necessitates justification for why this particular object warrants intensive follow-up. If it is likely just an unusual comet, perhaps resources should be directed elsewhere. However, if there exists even a small probability of it being something more significant, the potential scientific reward could justify the investment. These are judgment calls without definitive correct answers. What will be the outcome if 3I Atlas ultimately proves to be an unusual but natural comet, and we have spent months speculating about artificial origins? Some will argue that time and credibility were wasted. Others will contend that the process of seriously investigating the possibility was valuable, leading to the development of improved criteria for distinguishing natural from artificial phenomena and pushing the boundaries of the questions we are willing to ask. Both perspectives hold merit. And what if, and I wish to stress that this remains a significant hypothetical, what if there is validity to the artificial hypothesis? What if future observations reveal unmistakable signs of manufacture, engineering, or deliberate construction? The implications would ripple through every field of human knowledge. We would possess proof that intelligent life exists, or has existed, elsewhere in the galaxy. We would have tangible evidence, not merely radio signals. We could potentially gain access to materials and technologies developed under vastly different evolutionary and cultural circumstances. The scientific, philosophical, and cultural impact would be immense. However, we have not reached that point. What we currently have is a mystery, disagreement, incomplete data, and the slow, arduous machinery of science endeavoring to comprehend observations that defy our expectations. In the subsequent section, we will broaden our perspective from this specific object to understand its place within wider trends in astronomy and space science during the year 2025. This is because 3I Atlas is not the sole discovery challenging our assumptions this year. Part 11. Recent Discovery, Exoplanet Super-Venus Revisited. While our attention has been captivated by 3I Atlas's passage through our solar system, astronomers studying exoplanets, planets orbiting stars other than our Sun, have been encountering their own category-defying surprises. One recent finding from 2025 exemplifies how our preconceptions regarding planetary composition and formation are being challenged on multiple fronts. The narrative of a newly characterized super-Venus offers a relevant parallel to our interstellar visitor, suggesting that unusual phenomena might be more prevalent in the cosmos than we previously imagined. The planet in question orbits a star approximately 150 light-years from Earth. Initial assessments indicated it was Venus-like, possessing a similar size and orbital distance from its star, presumably with a comparable composition. A rocky world, potentially featuring a dense atmosphere, superheated by its proximity to the Sun. Venus analogues are of interest because they aid in our understanding of planetary climate and habitability. Venus in our own solar system is a hellish environment, with surface temperatures capable of melting lead and atmospheric pressure 90 times that of Earth's. However, it may not have always been this way. Comprehending the evolutionary paths of Venus-like worlds helps us consider the spectrum of planetary outcomes and what factors contribute to a planet's habitability versus its hostility. Consequently, astronomers directed powerful instruments toward this distant Venus analog, anticipating confirmation of their existing models. They meticulously measured its transit, the slight dimming of the star's light as the planet crosses in front of it. They analyzed the starlight filtering through the planet's atmosphere during transit, searching for spectroscopic signatures indicative of atmospheric composition. They determined the planet's mass by observing the subtle wobble it induces in its star's movement. Upon consolidating all the data, an anomaly emerged. The planet's density was significantly higher than anticipated. Venus has a density of approximately 5.2 grams per cubic centimeter, consistent with a rocky world containing an iron core. This super-Venus exhibited a notably greater density, implying a composition richer in heavy elements. This suggests more iron, possibly substantial amounts of nickel or other dense metals, and potentially less of the lighter silicate rock that constitutes planetary mantles. It was as if a standard rocky planet had had a considerable portion of its rocky material replaced with metal. This immediately raises questions for planetary formation theories. Rocky planets originate through accretion, where dust and small bodies in a protoplanetary disk collide and coalesce, gradually accumulating into larger celestial bodies. The composition of these planets is dictated by the materials available in the region of the disk where they formed. Closer to the star, temperatures are elevated, favoring materials with high condensation points, such as metals and refractory minerals. Further out, volatile ices and organic compounds are more prevalent. This establishes a compositional gradient across a planetary system. However, this super-Venus appeared to contradict these expectations. At its orbital distance, such a metal-rich composition would not be expected unless some unusual event occurred. Perhaps the planet formed at a greater distance and migrated inward, although this explanation does not readily account for the high metal content. Another possibility is that a massive collision stripped away lighter mantle material, leaving a disproportionately large metallic core. Alternatively, the protoplanetary disk itself might have possessed an unusual composition from its inception, being richer in metals than typical disks. Each of these explanations necessitates specific circumstances, and none is entirely satisfactory. Does this sound familiar? We are encountering a similar pattern with the observations of 3I Atlas, where data does not align with standard models, exhibiting a composition that appears incongruous with its circumstances, requiring the invocation of unique formation or alteration processes to reconcile the observations. This parallel is instructive. It suggests that we may be consistently underestimating the diversity of outcomes possible in planetary system formation. Consider the implications for our understanding of smaller bodies like comets and asteroids. If planets can exhibit widely varying compositions, even at similar orbital distances in different systems, then the smaller bodies within those systems, the residual debris from planet formation, should display comparable diversity. An interstellar object ejected from a metal-rich planetary system might bear no resemblance to the ice and rock comets familiar from our solar system. It could be predominantly metallic or carbonaceous, with minimal volatiles, simply because those were the abundant materials in its birthplace environment. This reframes 3I Atlas in an intriguing light. Perhaps it is not defying the established rules of cometary behavior. Instead, it might be adhering to the rules of a different planetary system, one where the raw materials for small body formation differed significantly from our own. Our solar system originated from a protoplanetary disk with a specific metallicity, a particular carbon-to-oxygen ratio, distinct temperature gradients, and a unique dynamical evolution. Other systems formed under different conditions, and consequently, their comets and asteroids may possess different typical compositions. The discovery of the supervenus also underscores the limited scope of our exoplanet sample. We have now characterized thousands of exoplanets, although most are large gas giants or hot super-Earths, which are easier to detect. We are only beginning to comprehensively analyze the composition of rocky planets. Each new measurement reveals surprising diversity. In terms of interstellar objects, we have confirmed the arrival of exactly 3 visitors. This is not a representative sample. It is barely sufficient to establish that interstellar objects exist. Drawing conclusions about what constitutes normal versus anomalous based on only 3 examples is epistemologically precarious. Consider this thought experiment. Imagine an alien civilization studying the small bodies within their solar system for centuries. They have observed thousands of comets and asteroids, all formed from their local protoplanetary disk. They have developed models defining what comets are, how they behave, and their constituent materials. Then, an interstellar visitor arrives from our solar system, let us say, a Jupiter family comet. Typical by our standards, it might appear utterly bizarre to them. Its ice composition would be incorrect, the rock-to-ice ratio would be wrong, and it would contain strange organic molecules absent in their local comets. They might debate whether it is even a comet at all, or if it belongs to another class of object. The point is that normal is defined by one's local sample, and the universe may not adhere to those localized definitions. This does not resolve the mystery surrounding 3I Atlas, but it does provide context. We are currently experiencing a period where multiple discoveries across various astronomical domains are challenging our fundamental assumptions. Planets are not as standardized as we once believed, and it appears that small bodies are similarly diverse. The cosmos is more varied and inventive in its construction than our models had anticipated. This is simultaneously humbling and exhilarating. It signifies that there is more to discover, more categories to delineate, and more physical regimes to explore. It also implies that we must exercise caution in dismissing anomalies too readily. When we encounter something that deviates from our established frameworks, whether it be a superdense Venus analog or a comet exhibiting acceleration without outgassing, our initial inclination is often to force it into the nearest available category or to invoke special circumstances to preserve our existing models. However, on occasion, the appropriate response is to seriously consider that our categories might be incomplete, that the universe harbors phenomena we have not yet adequately conceptualized. The history of science is replete with instances where anomalies necessitated paradigm shifts. Mercury's orbital precession revealed general relativity. The spectrum of black body radiation unveiled quantum mechanics, and the rotation curves of galaxies pointed to the existence of dark matter. Not every anomaly leads to a revolution, but those that do are the drivers of scientific advancement. Therefore, as we continue our investigation of 3I Atlas, let us keep this broader context in mind. We are not merely studying one peculiar object, we are probing the limits of our understanding across the board. From planetary composition to the physics of small bodies to the diversity of outcomes in planetary system formation, each probe reveals that the universe is vaster, stranger, and more varied than we ever imagined. Part 12. AI-augmented asteroid and comet detection and classification. The sheer volume of data generated in modern astronomy presents both an opportunity and a crisis. The opportunity lies in our unprecedented ability to observe the sky with remarkable depth, temporal coverage, and wavelength range. The crisis stems from the fact that the data volume far exceeds human capacity for analysis. This is where artificial intelligence enters the picture, and its role is particularly relevant for objects like 3I Atlas, which represent rare anomalous phenomena easily lost amidst routine observations. Understanding how AI is transforming small-body astronomy helps us appreciate both what we are discovering and what we might be overlooking. Let us begin by considering the scale of the challenge. Traditional astronomical surveys captured perhaps thousands of images each night, with each image containing hundreds to thousands of objects, stars, galaxies, asteroids, and artifacts. Human astronomers or small teams could review these images, flagging interesting objects for further investigation. However, modern surveys operate on an entirely different level. The forthcoming Vera C. Rubin Observatory, slated to commence full operations shortly, will image the entire visible sky every few nights using an 8.4-meter telescope equipped with a camera boasting 3.2 billion pixels. Each night, it is projected to generate approximately 20 terabytes of raw data, detecting roughly 10 million transient or moving objects. That is not a typographical error. 10 million alerts per night, each potentially representing something of interest: an asteroid, a supernova, a variable star, a cosmic ray impact, or an instrumental artifact. No team of humans can possibly review 10 million alerts per night and make informed decisions about which ones warrant follow-up. Automation is essential. Machine learning algorithms, trained to recognize patterns, classify objects, and flag anomalies, are indispensable. This is where AI plays a pivotal role, revolutionizing astronomical practices. The fundamental methodology employs supervised learning. A neural network is trained on labeled examples. This is an asteroid. This is a distant galaxy. This is a cosmic ray. This is instrumental noise. The network learns to identify features within images and spectra that differentiate these categories. Once trained, it can automatically process new observations, assigning classifications and confidence levels. For routine objects, this approach is remarkably effective. AI classifiers can identify asteroids, determine their approximate orbits, and flag those that may be near-Earth objects requiring immediate tracking. They can detect supernovae in distant galaxies, classify variable stars, and identify gravitational lensing events, all automatically, at scale, with accuracy rivaling or surpassing that of human experts. However, here lies a fascinating paradox. AI excels at identifying what it has been trained to recognize, yet it can be profoundly ineffective at detecting things that do not conform to its training categories. If a network is trained exclusively on images of typical solar system asteroids and comets, it will learn to recognize what is considered typical. When an interstellar object like 3I Atlas appears, behaving unlike either category, the AI might misclassify it, assign it a low priority, or flag it as a probable false detection. The very efficiency that enables AI to process millions of observations can also render it oblivious to the genuinely novel. This is why anomaly detection represents a distinct and critical approach. Instead of asking, "To which category does this belong?" anomaly detection asks, "How does this differ from everything we have observed previously?" This involves unsupervised learning. The algorithm is not provided with labeled categories. Instead, it learns the natural distribution of properties within the data and flags outliers. An object exhibiting unusual motion, a strange color, anomalous brightness variations, or any other property situated far from the norm would be automatically flagged. 3I Atlas was initially discovered by the Atlas Survey, which utilizes automated detection but relies on classical algorithms rather than deep learning. The object was flagged due to its trajectory. It was not moving like a solar system body, suggesting an origin from interstellar space. However, one must consider whether this object, had it arrived a few years from now, when AI classifiers are managing the majority of the survey workload, would have been promptly flagged or potentially misclassified, delaying follow-up while more routine objects received telescope time. These are not purely hypothetical concerns. Research groups are actively developing AI systems for the era of the Vera C. Rubin Observatory. One approach involves training networks on simulated interstellar objects, teaching the AI to recognize distinguishing features. Another method employs anomaly detection to automatically flag anything unusual, irrespective of whether it fits expected categories. A third approach combines classification and anomaly detection in a hybrid system, efficiently classifying routine objects while maintaining a separate anomaly stream for objects that do not fit well into any predefined category. The implications extend beyond the mere detection of interstellar visitors. Artificial intelligence is currently being developed to identify sudden outbursts from comets, to detect active asteroids, to spot unusual spectral signatures, and to correlate observations across multiple wavelengths. In theory, an AI system could have flagged 3I Atlas, not just for its peculiar movement, but for the discrepancy between its observed acceleration and its visual appearance. It's possible to train a neural network to recognize the signs of gas release, the formation of a coma, the development of a tail, and characteristic brightness fluctuations, and then flag objects exhibiting acceleration without these signatures as anomalous. This kind of multivariate anomaly detection can uncover subtle oddities that human observers might overlook. However, significant challenges exist. AI systems can be fragile, failing in unpredictable ways when encountering edge cases. They may also inherit biases from the data they are trained on. For instance, if an AI is trained primarily on bright objects because they are well studied, it might perform poorly on faint objects. Additionally, AI can generate false positives, inundating astronomers with spurious alerts. Furthermore, AI decision-making processes are often opaque, making it difficult to understand the reasoning behind their conclusions based on learned patterns. When an AI identifies an object as anomalous, comprehending the basis for that determination can be problematic. There's also the fundamental question of whether AI might miss truly groundbreaking objects simply because they are too dissimilar to anything previously encountered. If an artificial interstellar probe, designed by an intelligence with engineering principles far beyond human conception, were to traverse our solar system, it might produce observational signatures unlike any natural object. An AI trained solely on natural phenomena might not recognize it as significant at all. It could be misclassified as noise, an instrumental artifact, or something too peculiar to fit any existing model and therefore deemed erroneous. This represents the less desirable aspect of automation: efficiency achieved at the expense of serendipity and classification prioritized over discovery. Human intuition and expert judgment remain indispensable. The optimal approach involves integrating AI's efficiency with human oversight. Let the algorithms manage the vast majority of routine objects, but present genuinely strange ones for human expert evaluation. This necessitates the development of tools that enable astronomers to easily review AI decisions, investigate flagged objects, and override classifications when expert knowledge dictates otherwise. It also requires fostering a culture of curiosity where unusual objects are not simply dismissed as errors, but are thoroughly investigated to understand what they reveal. Looking ahead, the role of AI in astronomy is poised for continued expansion. The sheer volume of astronomical data is growing at a rate that outpaces the human workforce. This presents both opportunities and responsibilities. The opportunity lies in discovering rare objects, identifying subtle patterns, and processing information efficiently at scales impossible for unaided humans. The responsibility involves ensuring that important phenomena are not systematically missed, preserving the human elements of curiosity and intuition, and maintaining humility regarding the limitations of our models and classifications. 3i Atlas serves as a crucial test case for our preparedness in managing this transition. We have detected it and are actively studying it, yet we are also grappling with its perplexing nature. The AI tools we develop in the coming years will determine whether future interstellar visitors receive the attention they warrant or pass through unnoticed. Part 13 delves into a storm that should have fundamentally altered our understanding. Picture this: early November of 2025. The sun unleashes one of its most ferocious outbursts in years. Jets of plasma erupt outward at speeds approaching 1 million miles per hour. Magnetic fields twist, snap, and reconnect. Solar storms so intense that they paint auroras across latitudes that rarely experience them. And right at the heart of this cosmic tempest was 3i Atlas, having recently completed its closest passage to our star. Any typical comet would have reacted violently to such conditions. It's crucial to understand the relationship between solar storms and small celestial bodies. The sun is not merely a static source of light and heat, it is a dynamic entity. During periods of heightened activity, it expels massive clouds of charged particles into space, known as coronal mass ejections, which carry their own complex magnetic fields. When these storms impact a comet, several phenomena occur concurrently. The charged particles interact with any surrounding gas, ionizing it and causing it to glow. The magnetic fields can couple with the comet's induced magnetosphere, generating electrical currents that heat the surface. Perhaps most dramatically, the increased flux of high-energy particles can physically ablate material from the surface, atom by atom, akin to molecular-level sandblasting. A paper published in March of 2025 by researchers at the Southwest Research Institute meticulously examined this precise phenomenon. They investigated the impact of solar storms on the volatile activity of small bodies during their perihelion passage. Their models were both elegant and comprehensive. Introducing a typical comet into a powerful solar storm environment should result in enhanced gas release, surges in dust ejection, and even sudden outbursts as pockets of subsurface ice flash into vapor. The storm does not simply heat the surface passively. It actively strips away material through a process called ion sputtering, where energetic particles physically dislodge molecules from the comet's surface. The study analyzed historical data from comets that approached the Sun during active solar periods. The correlation was unequivocal. A solar storm equates to heightened activity, and an increased particle flux leads to enhanced gas release. This fundamental physics has been consistently confirmed across numerous celestial bodies over decades of observation. 3i Atlas encountered these exact conditions in late October and early November of 2025. The Sun was in an active phase, and solar storms were propagating outward. Some of these storms would have intersected the object's trajectory within days of its perihelion, a time when its surface was already intensely heated and any volatile ices should have been sublimating rapidly. The outcome was striking. Nothing. No tail, no coma, no outburst. This is where the anomaly becomes truly perplexing. We are not discussing a minor deviation. We are observing an object that defied one of the most robust predictions in cometary science. Solar storms are expected to trigger activity, and they invariably have. Every comet studied during an active solar period has exhibited some response, such as increased brightness, tail expansion, or spikes in dust production. The underlying physics is too fundamental to disregard unless the object simply lacks the material to react. Consider the implications. Either 3I Atlas possesses a surface composition so unusual that solar storms slide off it, or it is entirely devoid of volatiles. Both possibilities are extraordinary and challenge our established assumptions. Some researchers are now postulating previously unobserved surface states. What if the object developed a sort of metallic shell during its journey through interstellar space? Cosmic rays bombarding the surface for millions of years could have altered its chemistry, creating a hardened crust resistant to both thermal and particle-driven erosion. Alternatively, perhaps it is not a crust, but the object's inherent composition, a mass of metal-rich material possibly originating from a disrupted planetary core in another star system, enveloped by a thin layer of carbonaceous compounds. Either scenario would account for its resistance to solar storm effects. Metals do not sublimate at these temperatures, and carbon compounds can exhibit remarkable stability. If the surface is predominantly composed of these materials, rather than water ice or other volatiles, then solar storms would have minimal impact. It would be akin to attempting to erode something that simply will not budge under those conditions. The implications of this are far-reaching. Near-small body physics, which we believe to be well understood, might be far more dependent on surface composition than we previously realized. Our models were constructed based on observable objects, icy comets, rocky asteroids, and their combinations. But what about the objects we have yet to encounter? What about compositional categories we have not yet identified? 3I Atlas might be revealing a significant blind spot in our comprehension. We assumed all comets would react to solar heating and solar storms in predictable ways because every comet we had studied behaved in precisely that manner. However, this is a case of selection bias. We were studying objects that had survived long enough to become observable, those that outgassed sufficiently to develop tails, those that conformed to our preconceived notions. Our understanding of comet-sun interactions is being fundamentally challenged by this single object. It is indeed a single data point, but one that stubbornly refuses to behave as expected. In science, outliers are often the most informative. They compel us to expand our theories, question our assumptions, and re-examine established problems with fresh perspectives. However, there exists another possibility that we have not yet explored, an explanation that sounds like science fiction but has garnered significant scientific interest in recent years. What if we are not dealing with a natural object at all? Part 14 discusses the intersection of science and speculation. Let us revisit October of 2017, the discovery of Oumuamua, the first confirmed interstellar object to transit our solar system. Within weeks, the scientific community was abuzz. Within months, serious researchers at reputable institutions began posing a question that would have seemed preposterous just years prior. Could it be artificial? The notion, while initially surprising, was not entirely unfounded. Oumuamua was peculiar, exhibiting an unusually elongated shape, remarkable reflectivity, and an acceleration pattern that did not quite align with standard outgassing models. Harvard astronomer Avi Loeb suggested it might be a light sail, a manufactured object propelled by photon pressure. While the scientific community largely dismissed this hypothesis, the seed of the idea was sown. We had entered an era where interstellar visitors warranted scrutiny not only for their natural properties, but also for potential artificial signatures. Fast forward to 2025, and this scrutiny has become a systematic endeavor. Multiple research groups, including teams at the SETI Institute, have developed specific protocols for monitoring interstellar objects. When 3I Atlas was identified as a potential interstellar visitor, these protocols were immediately activated. Telescope time was allocated, radio dishes were directed toward the object's trajectory, and optical and infrared instruments were focused on its position, searching for any indicators of non-natural origins. The fundamental question is not whether we should investigate, but rather how to proceed and what specific signatures to seek. Differentiating between natural and artificial objects in space is more challenging than one might initially assume. Nature is capable of producing remarkably regular patterns. Crystalline structures, orbital resonances, and even the hexagonal storms observed on Saturn, while appearing designed, emerge from basic physical laws. Conversely, not all artificial objects exhibit obvious signs of manufacture. A derelict probe drifting through space for millions of years could become pitted, darkened, and eroded to the point where it resembles a natural rock. So, what specific signatures should we be looking for? Several categories emerge. First, structured motion. If an object tumbles in a manner suggesting attitude control, or if its acceleration pattern implies propulsion rather than outgassing, that is a significant indicator. Second, electromagnetic emissions. This includes narrow-band radio signals, laser pulses, or any form of transmission that does not occur naturally. Third, material properties. Highly reflective surfaces or unusual spectral signatures suggesting engineered alloys or composites are of interest. Fourth, geometry. Large area-to-mass ratios that exceed typical natural occurrences, or shapes implying function rather than random formation. 3i Atlas exhibits some of these characteristics. Its lack of outgassing, despite measurable acceleration, is unusual. Its potential metal and carbon composition is anomalous for a comet. Its compact, star-like appearance without any diffuse envelope is peculiar. While none of these individually prove artificiality, collectively they present a profile that demands attention. The Breakthrough Listen initiative, which employs radio telescopes to search for signs of intelligent life, added 3i Atlas to its target list in late October 2025. They are scanning the object across multiple frequency bands, seeking any signal that might indicate technological origins. Thus far, the results have been negative. No narrow-band emissions and no obvious transmissions. However, the absence of evidence is not evidence of absence. A derelict probe might not necessarily be broadcasting, and a fragment of manufactured material would not be sending signals at all. This is where scientific caution becomes paramount. We cannot leap from "this object is unusual" to "this object is artificial" without extraordinary evidence. The burden of proof is immense, and rightfully so. Extraordinary claims require extraordinary verification. Every conceivable natural explanation must be thoroughly explored before we seriously entertain an artificial hypothesis. Nevertheless, let us entertain it as speculation, clearly labeled as such, because this is where the narrative becomes truly fascinating. If 3i Atlas were artificial, what might it be? Option 1. A derelict probe. It could be the equivalent of our Voyager spacecraft, launched millions of years ago by some civilization, now tumbling through the galaxy with its systems long defunct and its mission forgotten even by its creators. It would simply be a piece of ancient technology, a cosmic fossil. Option 2. A manufactured fragment. Perhaps not an intact probe, but a piece of something larger, a component of planetary engineering, a fragment from a Dyson swarm, or debris from an industrial accident on a scale we can barely comprehend. It would be artificial, yes, but not intentionally sent anywhere, simply drifting detritus. Option 3. And this is where it becomes truly strange, an interstellar buoy. It could be a deliberately placed marker or a relay station, part of a network we cannot perceive. Perhaps it is not transmitting because we are not listening on the correct frequency, or because it only activates under specific conditions, or because it is simply awaiting an action from us that has yet to occur. All these possibilities sound like science fiction, and all are statistically improbable. However, the universe is vast and ancient. If technological civilizations exist elsewhere, and if even a small fraction of them engage in interstellar activity, then finding their artifacts is not impossible, merely improbable. Here's the engaging aspect. We are no longer solely astronomers. We are cosmic detectives. We are gathering evidence, systematically ruling out possibilities, and posing questions that blur the lines between astrophysics and something entirely different. Regardless of whether 3I Atlas is natural or artificial, the fact that we are seriously considering the question signifies a paradigm shift in how we approach interstellar objects. And the investigation continues. New data arrives weekly. Observatories worldwide and in orbit are tracking this object, meticulously measuring every discernible aspect. What we learn may rewrite our understanding of small body composition, or it may rewrite something far more profound. In either case, the next few months will be critical because 3I Atlas will not remain visible indefinitely. Part 15 addresses the closing window of opportunity. Time is our adversary in this scenario. 3I Atlas reached its closest proximity to the Sun in late October of 2025. Since then, it has been accelerating outward, moving away from both the Sun and Earth, diminishing in brightness with each passing day. Within months, it will be beyond the reach of most ground-based telescopes. Within 1 to 2 years, only the most powerful instruments will be capable of detecting it. Eventually, it will fade into the darkness between the stars, becoming another enigma that passed through, leaving us with more questions than answers, unless we act decisively. The James Webb Space Telescope has scheduled observations of the object for December of 2025 and January of 2026. These observations will involve deep imaging and spectroscopy, using instruments sensitive enough to detect trace elements and organic molecules should they be present. This could provide the definitive data to resolve the composition question. Will it reveal metals and carbon, or have we been misinterpreting the limited spectral data we have gathered thus far? The Webb telescope is expected to provide clarity. Ground-based observatories are also mobilizing. The extremely large telescope in Chile and the giant Magellan telescope, both of which commenced operations in the early 2020s, are planning follow-up observations. Their massive mirrors possess the capacity to collect sufficient light to study 3I Atlas, even as its brightness wanes. These observations will focus on rotation rates, surface features if detectable, and continued monitoring for any indication of gas release or activity. There have even been preliminary discussions regarding the deployment of small satellite missions, such as CubeSats or similar platforms equipped with cameras and spectrometers, launched on trajectories that could intercept or at least observe 3I Atlas from a closer vantage point. These missions are ambitious, presenting significant technical and financial challenges, but the scientific reward would be immense. Nothing surpasses in situ observation, and nothing answers questions quite like being physically present. Furthermore, the ultimate aspiration is a sample return or rendezvous mission. Imagine a spacecraft successfully intercepting 3I Atlas, matching its velocity, and studying it up close for an extended period. Envision that spacecraft collecting physical samples, fragments of an interstellar traveler, and returning them to Earth for laboratory analysis. We would glean more from a single gram of 3I Atlas than from thousands of hours of telescope observation. While such a mission is not currently funded or planned, it is a subject of discussion. Space agencies are observing, private companies are watching, and the appetite for interstellar object missions is growing. 3i Atlas represents precisely the kind of target that could justify such an investment. What would we learn if the object proves to be indeed metal-rich, containing iron, nickel, and carbon in unusual forms? We would be compelled to establish a new category within our taxonomy of small bodies. Currently, we classify objects as comets, asteroids, Kuiper belt objects, and interplanetary dust. Where would a metal and carbon-rich interstellar visitor fit? How would such objects form? Are they remnants from planetary collisions in other star systems, or do they represent something entirely novel that we have not encountered in our own solar system? The implications for planet formation models would be substantial. If other star systems produce metal-rich ejecta that escapes into interstellar space, then the composition of planetary systems might exhibit far greater diversity than we currently believe. Alternatively, our own solar system might be the outlier, unusually depleted in certain elements, and 3i Atlas could be revealing the typical composition of planetary systems elsewhere. Even if 3i Atlas ultimately proves to be entirely natural and explainable by known physics, its vastly different behavior compared to every comet we have studied necessitates an expansion of our expectations. We must be prepared for surprises and accept that the universe is more varied, more enigmatic, and more wonderfully complex than our current theories permit. And more surprises are indeed on the horizon. The Vera C. Rubin Observatory in Chile, equipped with its large synoptic survey telescope, commenced full operations in 2023. It systematically scans the entire visible sky every few nights, cataloging all celestial bodies that exhibit movement or change. Its primary objective is the study of dark energy and dark matter. However, a significant positive outcome is its capacity to discover interstellar objects, and a considerable number of them. Projections indicate that the Rubin Observatory will detect one interstellar visitor annually, and potentially more. We are entering an era of interstellar object statistics. Instead of studying Oumuamua, Borisov, and 3 Atlas as isolated curiosities, we will possess sample sizes large enough to draw statistically significant conclusions. We will begin to ascertain what is typical, what is rare, and the range of compositions and behaviors that exist throughout the galaxy. This marks the advent of Interstellar Object Population 2.0, the era when we cease to be surprised by every visitor and begin to build a comprehensive understanding of what travels between the stars. However, there is a human dimension to this narrative that should not be overlooked. As November of the year 2025 unfolds, humanity finds itself observing an entity originating from a celestial body beyond our own solar system, traversing the cosmic expanse of our immediate galactic vicinity. This visitor, a construct born around a sun alien to ours, has journeyed for immeasurable spans of time through the profound emptiness, carrying within its very composition the elemental traces of distant extraterrestrial worlds, and we are actively engaged in its real-time examination. Scientific findings are being disseminated on a weekly basis. Observational campaigns are being meticulously coordinated across multiple continents. Scholars are engaged in spirited discussions concerning interpretations, diligently refining their theoretical constructs, and proposing avenues for further inquiry. This represents the very essence of scientific endeavor in action, a process that is inherently complex, thrilling, and marked by inherent ambiguity. No established text currently holds the definitive explanation, for such an explanation has yet to be formulated. We are collectively authoring this understanding piece by piece through each observation, each published research paper, and each dedicated night spent peering through our telescopes. Regardless of whether Oumuamua proves to be a metallically rich fragment of a disintegrated exoplanet, a carbon-encased remnant of cosmic chemical processes occurring between stars, or something even more peculiar, it has bestowed upon us an extraordinary gift. It has afforded us a fleeting visitation, a rare aperture into the broader tapestry of the galaxy, and a vital reminder that our solar system is not an isolated entity. It serves to reinforce the understanding that we inhabit a universe teeming with objects that traverse the interstellar distances and that visitors can arrive bearing enigmas. It is imperative that we capitalize on this unique opportunity. The chance is rapidly diminishing. Oumuamua's presence is fading, yet the profound questions it evokes will undoubtedly persist long after it vanishes into the immeasurable darkness. Therefore, what do you surmise it to be? A celestial wanderer unlike any previously catalogued? A fragment originating from the core of an alien planet? A natural phenomenon that fundamentally challenges our existing classifications? And what further revelations await us when the data from the James Webb Telescope becomes available? When the subsequent phase of observations reaches completion, and when another interstellar sojourner appears within the view of our instruments, the cosmos is extending to us emissaries, peculiar travelers from the vast gulfs separating the stars. The crucial question is whether we possess the readiness to comprehend their messages, whether we exhibit the courage to look beyond the familiar and embrace the extraordinary. Remain attentive. Keep abreast of the official data releases. Scrutinize the scientific publications, for this unfolding narrative is presently transpiring, and you are a witness to its unfolding. Oumuamua is now hurtling away from us, receding into the void, carrying its intrinsic mysteries back into the cosmic deep. But before its departure, before its faint glow extinguishes entirely, we possess a final opportunity to grasp the significance of our observations. One final moment to unravel the puzzle, one final chance to ascertain what traverses the darkness that lies between the stars.